following program is brought to you by Caltech.
Okay, so next up we have Steve Furlanetto from UCLA, who is going to talk about the redshifted 21 centimeter hyperfine line from neutral hydrogen, as he and Chris have agreed. So Chris, Steve, was a graduate student with Avi Loeb at the CFA, and he was a postdoc here at Caltech in the TAPER group, and now he's a faculty member at UCLA. He's very, very involved in the 21 centimeter world. And he's going to cover mostly some theoretical aspects, continuing our trail of hydrogen discussion. And I see from the pictures he has on his cover slide, he'll at least touch on a few of the experiments. All right, so take it away, Steve.
Everybody hear me? OK, so I'm going to be telling you about the 21 centimeter transition, as Jed said. I'm going to give an overview of the basic physics, kind of the atomic physics that you've heard about earlier, but spun a little differently. Then I'll briefly cover the instruments that will be used and are being used to make these measurements, because they're very different than what most of you who work in the CMB world might be used to. And then I'll go through in some detail more of the astrophysics and how that ties into the fundamental physics I've already talked about. OK, so we're talking about the hyperfine transition. For those of you who are new to this game, that's when the magnetic moments of the proton and electron go from being aligned to anti-aligned. That's a very small energy difference corresponding to a 21 centimeter wavelength photon, or 1.42 gigahertz. Obviously, it's very weak because it's hyperfine. But there's a whole lot of neutral hydrogen in the universe, so we're hoping to use that to actually measure this. So there are 4 advantages to using this particular line. The first is that it's available over the entire sky. So the traditional way that astrophysicists study the intergalactic medium is through what's called the Lymanalpha forest, which involves quasar spectra in the UV, or redshifted UV. The problem with that is you need a quasar as your light source. Now we're talking about a radio line, low frequency radio, and so you have a background light source everywhere. That's the CMB. So we can make this measurement over the entire sky. Not only that, but we're looking at a specific spectral line. And so each observed wavelength will correspond to a different emission distance from us. So a photon emitted here, redshifting to the observer over there, its wavelength will change by a certain amount determined by its path length, whereas a photon that starts over here has a longer path length, so redshifts more, ends up at a different frequency. So we can separate out the different distances from us. And so unlike the CMB, which is one image of the sky, we get a series of images of the sky at different distances or times. And so the ultimate goal is to make movies like this, okay, of the 21 centimeter signal. So here the color scale is the brightness in this particular transition. And the black blobs that are growing up are the ionized bubbles around the first galaxies in the universe that expand to fill the universe, and by redshift of 5 or 6 or so have ionized all of the gas. The third advantage is that for many, or at least an advantage for many applications, is that we're directly measuring what's happening between the galaxies and not using the galaxies as an indirect tracer of what's going on for most of the matter in the universe. So redshifts of 10, 6, 10, 20, whatever you're looking at, only a few % at most of the baryons are actually inside of galaxies. So by looking at the hydrogen that remains between the galaxies, we're really getting a much more unbiased view of matter in the universe. And the final quote-unquote advantage is that this is a very weak transition. And the problem is that there's so much neutral hydrogen in the universe that if you use a highly resonant transition like Lymanalpha, you very, very quickly run into complete saturation in your signal. So the optical depth in Lymanalpha at these redshifts is like 300,000. Okay? With a weak line like the hyperfine line, the optical depth is like 1%. Right? So you're in the signal limited regime, but on the other hand, you're sensitive to order unity changes in the neutral fraction, for example, or the density, which are the kinds of things you want to actually search for. OK, so here is, I think, the only equation that you'll see in this talk. This is the signal in the 21 centimeter line. We measure it in units of brightness temperature, much like the CMB. On average, we're talking about something like 20 millikelvin. All right, so that, to those of you in the CMB world, that may seem extraordinarily large and very easy to see, but I'll show you it's actually really difficult. And there are 4 factors that affect the brightness of this signal. The first, this one here, is the neutral fraction. Obviously, no neutral gas, no signal. The second one right here, 1 plus delta, that's the density of the universe in units of the mean density. Okay, more stuff, more absorption or emission. The third factor is the complicated one. This is temperature, and I'll get back to that in a second. The fourth factor is velocity. Okay, and the idea here is that we're using observed wavelength as a proxy for distance. Right? And in that mapping, you need to assume that the gas is expanding at the Hubble rate. Right? If the gas is expanding at some other rate, then there's going to be an error in your mapping from frequency to distance. And that's going to give you distortions. Right? But it turns out those distortions are actually really useful. So if you imagine that this is some overdense region in the universe with more matter than average, okay, then there's more gravity as well. This little piece of the universe is expanding more slowly than average. Okay, so we have smaller velocities coming toward and away from the observer. The observer is down here. All right, so when you make your mapping from frequency to distance, you're going to think that these two sides are closer together than they really are because their velocities are less than the Hubble rate. And so this region, which has more matter to begin with, appears to get squashed farther when you look at it. Right? So this effect actually amplifies the fluctuations that are already there. Conversely, if you have an underdense void, less matter than average, expanding faster than average, you stretch things out, and again, you amplify the underdensity that was already there. There are 3 interesting things about this. The first is that it boosts your signal. That helps because we're in the weak signal regime. The second is that that boost is actually not isotropic. Right? It's only the velocities along the line of sight that we're sensitive to because we're not using velocities to map the plane of the sky over here. Okay? So you get this amplification only along the line of sight. And so if you can measure the difference between the fluctuations on the plane of the sky and along the line of sight, you get extra information. And in principle, the extra information that you get is just depending on the gravity of the matter fluctuations. That's what's driving the difference in velocity. Right? Astrophysical effects very rarely affect velocities. So in principle, if you could measure the strength of these anisotropic distortions, you get a sensitive probe of the dark matter fluctuations themselves. In practice, unfortunately, this is more difficult than that because I'll briefly touch on this later, but during the era that we can most easily study, the ionized fraction fluctuations actually mask this stuff. Right? You have to go farther back to study these. All right, so that's this last factor, the velocity factor. Now I want to get back to the temperature factor here. The temperatures that we care about is this T sub s. That's called the spin temperature, which is the excitation temperature of the 21 centimeter transition itself. And remember, we're observing this transition relative to the CMB behind it. Okay? And so it's the temperature difference between the excitation temperature of the 21 centimeter line and the CMB. T background is the CMB temperature that will affect the strength of the signal. Okay? So what sets the spin temperature? All right, well, if you're very early on in the history of the universe, then collisions between neutral hydrogen atoms are common because the density is large. And so collisions will set this spin temperature. Once the first galaxies form, or around the time the first galaxies form, it turns out that the universe's density has fallen far enough for collisions to be inefficient. They don't help you. All right, so that would mean that the spin temperature goes to the CMB temperature, and that would mean that this whole factor would go to 0, because the only thing that can affect the spin temperature are the CMB photons. Okay, but once the first galaxies start to form, you get a new mechanism, which is called the Woutheisen field mechanism after the first 2 people to propose it. All right, and it's absorbing and re-emitting an ultraviolet photon to get a hyperfine transition. Okay, so here are the hyperfine splittings of the ground state of hydrogen. And here are those of the 2p state. All right, so suppose you begin down here in the singlet state. When you absorb a Lymanalpha photon, okay, and you jump up to that 2p level, the electric dipole selection rules allow you to go only to these 2 middle states. Okay? Now you're in an excited state. You're going to decay in a nanosecond or so. All right, but now these selection rules allow you to go back to the triplet state of the 1s level. So essentially, you've made a hyperfine transition by absorbing and re-emitting that Lymanalpha photon. Right? And if there are enough Lymanalpha photons in the universe relative to CMB photons, this mechanism will dominate and set the spin temperature. Okay? It turns out that because the universe is so optically thick to Lymanalpha, as we've already heard, the temperature to which this mechanism couples is just the normal gas temperature, the kinetic temperature. Okay? So if you have cold gas, then spin temperature is going to be less than CMB temperature. This factor is negative, and you get absorption. If you have hot gas, this temperature is going to be large compared to the CMB. This factor is positive. You get emission. So the next question is, what sets the gas temperature? All right, well, we've already heard that in the absence of anything fancy, the gas is cold. Okay? But once the first sources of light appear, things can get complicated very quickly, because X-rays can heat the IgM quite efficiently. So you have some X-ray source, whatever it might be. It spits out a high-energy photon. Those photons can travel megaparsec distances through the IgM. Eventually, they ionize usually a helium atom. That knocks off a high-energy electron, which then rattles around and knocks off some more electrons. Right? And so a lot of the excess energy of this electron ends up being translated into heat. Okay, so the CMB temperature is tens of Kelvin, so very little heating can dramatically affect this temperature factor. Okay? All right. The third radiation background, so far the Lymanalpha photons and the X-rays affect the 21 centimeter signal. The third is ionizing photons, which are going to obviously affect this first factor, the neutral fraction. Okay? And we call the process by which these ionizing photons fill the universe reionization. And basically what happens is the first galaxies form throughout this little piece of the universe. They produce stars or quasars or something that produces high-energy photons. Some of those high-energy photons leak out into the universe around them and produce little ionized bubbles, which are these little white blobs. Okay? As the galaxies grow up and merge together, right, those ionized bubbles get bigger and bigger and eventually fill the universe in what we call reionization. Okay? So this is we think now that reionization is kind of at the limit of where we can see the most distant galaxies. It happens somewhere between redshift of 10 or 6 or so. So at the tail end of the first billion years that we're talking about in this workshop. As such, it's the easiest and most accessible part of this 21 centimeter background. You're getting very big fluctuations between the ionized blobs and the neutral regions left over. Okay, and you're getting it the closest to us. So this is the first thing that we're trying to observe. Okay, so we have these three important radiation fields, and the question is which of them become important when? Okay, so the first thing is when does this Woutheisen field coupling mechanism kick in? Well, if you do the math, it turns out that it requires about one Lymanalpha photon in the universe per 10 atoms. Okay, each of those photons has about 10 eV. So your stars or UV source needs to produce 1 electron volt of energy per atom in the universe. Okay? When that happens, your spin temperature becomes your kinetic temperature of the gas. Okay? And hopefully, or at these redshifts, that is not equal to the CMB temperature. So this factor all of a sudden becomes non-zero, and you get a signal. Okay? Now, whether that signal is in absorption or emission depends on the X-rays. Okay, the CMB temperature is of order 100 Kelvin back then, or tens of Kelvin. So you need to heat the gas by 100 Kelvin to make a difference. Okay, that requires only about 1/100th of an electron volt per atom in the universe, which seems easy. Okay, however, most astrophysical sources are much more efficient UV emitters than X-ray emitters. All right, so if you say, I'm going to take normal star-forming galaxies at low redshift, I'm going to assume their properties also apply at high redshift. I'm going to look at when do I get this kicking in. Right? So when do I get 1 electron volt in Lymanalpha photons per atom? Well, it turns out that you only get about 10% of this heating, assuming normal X-ray emission. Okay? So the heating is probably, assuming that the low redshift properties are a good proxy for high redshift galaxies, which is most certainly wrong, but we don't know what else to do. In that case, this Woutheisen field coupling is going to kick in. And when you have about 10 times more stars, you're going to have enough heating to go from absorption here to emission. All right? The third thing you want to worry about is the ionizing photon field. All right? At first glance, you might think, well, this is not requiring much energy. You need of order 1 photon per atom in the universe, 1 ionizing photon, which means 10 electron volts or so per atom. Okay? That's actually about when this would happen. The trick is that those photons actually have to get out of the galaxies they start in. And that, at least at very low redshifts, is extremely difficult. Okay? It turns out that fewer than a few percent of ionizing photons can actually escape their galaxies at redshifts of 0 to a few. All right, so if that is the case at high redshift as well, all right, then this ionization is going to follow the heating by another order of magnitude in your stellar density. Okay, so the standard model is Woutheisen field coupling kicks in first, then heating, then ionization. All right, so what does that mean for the signal? Okay, well, here's the monopole in a very vanilla model of early structure formation by Jonathan Pritchard, who's right there. So ask him if you have any questions. He'll be talking in more detail about this, I think, tomorrow afternoon. So what happens is, so this is redshift, okay, going from early times at left to late times at right. And then here's the corresponding frequencies in the 21 centimeter line. Okay, so at very high redshifts, you get an absorption signal. This is just from the collisions of the atoms. Okay, we don't have any stars forming at redshift of 80, we think. Okay, so here is, there's no astrophysics that we know of, at least at redshift of 80. So if you could study the universe at this time, you would get a very sensitive probe of exotic physics, the same kinds of things that Jens was mentioning this morning, dark matter annihilation, et cetera. Okay? Once the first stars form, okay, so at the end of the dark ages, the signal vanishes because the collisions become inefficient. Spin temperature goes to CMB temperature, signal vanishes. Once the first stars form, they produce this Lymanalpha background that I was talking about. Okay, and that gives you your signal again. In this vanilla model, okay, the gas is cold, so you get absorption. All right, and that absorption gets deeper and deeper until the first black holes form. That is producing your X-ray background, presumably. And so you're going from absorption back up to emission. Okay? And then once you have enough heating, this reionization process starts, and that eventually more or less destroys your signal. Okay, so there's a lot of interesting astrophysics just in this monopole, because it's telling you all about when the first stars formed, what their properties were, when the first black holes formed, et cetera. Okay, but it's really only the first stage in the 21 centimeter transition. So there are now a large number of experiments that are just beginning to measure this, and even more planned for the future. And they have a wide range of kind of sizes. So the first two in red here, core and edges, are just trying to measure the monopole that I mentioned. They're kind of 2 or 3 person experiments, so quite small and compact. Judd is in charge of edges, so ask him if you have any questions. The ones in black here are all interferometers. And they're aiming not to measure the monopole, but to basically map the intergalactic medium as a function of redshift. So all of these are kind of $10 to $100 million class experiments. And they're all either sort of have their first science results coming out, or have, in this case, actually started to make real measurements. And then the ones in green down here are ones that are planned or at least hoped for the future. So Hera, the hydrogen epoch of reionization array, is sort of the next step in the evolution of these things. And we're hoping that this will sort of be happening in the next 10-ish years. All right, so if this is such an interesting measurement, why haven't people done it yet? Okay, well, there are 2 basic problems. And they both comes down to the fact that you have 1.4 gigahertz photon redshifted by a factor of 10 or so. Okay, so you're talking about 100 or 200 megahertz observed frequencies, and that's just a very difficult regime to work in. Okay, so this is the spectrum of the sky in that range in Sydney, Australia. And basically nowhere in here do you get down to the astronomical background, because you have FM radio stations, TVs, all kinds of communications. So you do the normal radio astronomy thing, and you go far away from civilization. So this is Narrabri, Australia, population 4,000. I think that's where Parkes is. Okay, and this diagonal line down here, that's the astronomical background. Okay, but you've still got an awful lot of interference in here. So you really have to go to the middle of nowhere to escape the terrestrial interference. This is Malura, Australia, population 4. Okay, and here you can actually get down to the background almost everywhere. And this is narrow interference, so the plan at least is to ignore, just work around it. The second and even worse problem is that this is far from the only astronomical signal out there. As all of you CMB people know, there are foregrounds from our own galaxy. So this is a map of the galaxy at 150 megahertz. Here's the galactic plane, galactic center. And the important thing here is that these contours are labeled in Kelvin. Okay, so the quietest part of the sky up here is about 200 Kelvin. Our signal is 20 millikelvin. So we're looking at picking out a signal that is 1 part in 10,000 of the total signal that you measure. Right, so we hope we can do that. And the way you do that is by saying that, well, the galactic foreground is almost all synchrotron and free-free. That's smooth in frequency space. Okay, so you subtract out the smooth component of the spectrum in each pixel. You're left with the bumpy part. Okay, the spectral line, the 21 centimeter spectral line is going to be bumpy. So that should be left. The other thing you're left with, unfortunately, is noise from a very bright foreground. Okay, and so it turns out that with the first generation experiments, we don't actually expect to be able to make maps. Okay, the signal to noise per pixel will be well below 1. Instead, we're going to try and do statistics. Just try and measure the power spectrum, okay, which, with the CMB, of course, is what gives you your interesting constraints anyway. All right, just a few words on these different experiments. There are a variety of approaches that people are taking. The first is to use a traditional radio astronomy telescope, by which I mean dishes. Okay, so this is the giant meter wave radio telescope in India. The advantage of dishes is that you get a very large collecting area very quickly. Okay, the problem is that the field of view of the dish points at something, and so the field of view of the dish is very small. And if you're doing statistics based on having a big volume that you're sampling, that's not so good. Okay. So the second way is to take the opposite extreme and say, well, we're talking about meter wavelengths here, and so you really only need a dipole to make a measurement. So this is the precision array to probe the epoch of Rihannasation. Okay, and it's using single dipoles. That's what this thing is actually 2 cross dipoles to get 2 polarizations, plus a ground screen. But this is their interferometer element. Okay, so very, very simple. The nice thing, the 2 nice things, one is that you get a very large field of view with a dipole. This is the sky coverage, essentially. So you get a very big volume quickly. The other advantage is that if you're doing this nasty foreground removal, it becomes much easier if you don't have any weird artifacts in your beam. And dipoles have very clean, simple beams, so it's easy to interpret that. The disadvantage is that to get this very faint signal, we need a big collecting area. Okay? And each of your dipoles is just a few meters across. So to build up 10,000 square meters of collecting area, you need an awful lot of dipoles. And if you're going to try and correlate them in an interferometer, your computational costs quickly become exorbitant. So the compromise approach between these two is to use what's called a phased array or stacked dipoles. And 2 experiments right now are doing that. One is LOFAR in the Netherlands. Okay, so this is one of their antennas. And the other is the Murchison Wide Field Array, which Judd and I are both involved in. And these are the equivalent of dipoles for the Murchison Wide Field Array. And what you do is you take a whole bunch of dipoles, you tile them together, you combine their signals via hardware, and then this tile of dipoles becomes your interferometer element. Okay? So you have kind of a compromise. You get a large collecting area by stacking the dipoles at the source. The compromise is that you're going to decrease your field of view. Okay? So this is meant to show the beam of MWA. It becomes narrower, although it's still a few hundred square degrees, so still pretty good by astronomical standards. And then the other disadvantage is that by doing this, you get nasty side lobes. And so your beam becomes more complicated, and removing all of these artifacts is going to be a little bit tougher. So all of these approaches are being taken by instruments that are out there now. I won't focus on the details. I just want to show you that actually things are moving along, and all of them have produced some sort of result. So the paper experiment, this is the single dipole one, has an all-sky map. Okay, so I think this is the galactic plane down here. All right. MLWA, which is one of these phased arrays, has a smaller field of view, but it's still, let's say these are in degrees. Okay, so tens of degrees by tens of degrees, pretty big. This is the Pictoris A cluster field, so each of these is a radio point source. All right, and then LOFAR is actually a general purpose low-frequency radio telescope. It has much bigger baselines than the rest, and so it can zoom in and make high-resolution maps. So this is one of their maps of a radio galaxy, a double-lobe radio galaxy with the hotspots up here. This is the VLA map, so you can see they're doing a really good job of getting what they expect to get. And then finally, the GMRT group, who use the dishes, are the farthest along. They've actually placed the first limits on the signal. Okay, so here is they're expressing it in terms of the angular power spectrum here. This is the most obvious prediction. Okay, and then these are using various different foreground removal techniques, the limits that they can place. So the best they can do is still about an order of magnitude above the expected signal. Okay, although they can rule out some more exotic models. The nice thing is that this is only 50 hours of integration. And so this is about where we would expect them to be after 50 hours. So there are no showstoppers yet. Still need to go farther, okay, but it's looking promising. All right, so again, getting back to the science, okay, the monopole is the first thing you hope to measure, or the easiest, the simplest thing one could hope to measure. Okay, at these very low frequencies in the dark ages, it's probably the only thing we're really ever going to measure. Okay, and as I said, this, the amplitude of this signal depends on the temperature of the background gas. And so it's going to be very sensitive to any energy injection process that's occurring from redshift of 1,000 to 100 or so. So all the things that Jens mentioned earlier today are also going to affect the 21 centimeter signal. The nice thing is that it's the baryons, and they're very cold. And so it's very sensitive to even very small energy injection mechanisms. All right, so the edges and core experiments are aiming to do this from the ground at probably the lower frequencies, higher frequencies, lower redshifts up here. And then we're making a proposal called DARE to try and look at the redshifts of, say, 35 to 10 or so from space. All right, so to say a little bit more about the physics of these later eras, I want to focus not on, well, this is the monopole in various models. So this is a different, this is my models instead of Jonathan, but essentially the same thing. The only difference is high redshift is at the right now, and low redshift is at the left. Okay, so you want to read it from right to left. To focus on these various eras of first stars, first black holes, and reionization, I want to talk about the fluctuations that these interferometers are aiming to measure. Okay. So when the first stars appear, okay, they're going to be very rare, and they're going to be highly clustered. And so what you basically end up with is a few bright UV sources. All right. Around each of them, you get a 1 over r squared fall off in the intensity of the Lymanalpha background. And so you're going to get strong coupling near those first galaxies. The gas is still cold there, so you get a big absorption signal here. If you're far away from those first galaxies, then you don't have a radiation background. So although the gas is still cold, it's invisible. All right, so you're going to get fluctuations in the sky, basically mapping out the locations of these first sources. Now, it turns out that if you wait long enough and you build up your radiation background throughout the universe, there's kind of a threshold effect that kicks in. So once you get a big enough Lymanalpha background, it doesn't matter anymore just how big it is. So even though you still expect a bigger radiation background near these first sources, it doesn't matter. You can't tell that in the 21 centimeter line. Right? So you get cold absorbing gas everywhere. And so compared to this earlier phase, where you're getting a contrast between cold absorption and cold invisible, the fluctuations are going to decrease as this era continues. All right, so here is, this is picking a particular scale and mapping out the fluctuation amplitude. The typical model is going to be this black curve right here. Okay, so you get an increase in the fluctuations as the first stars form. Once saturation hits, you're going to get a decrease in the fluctuations. All right, so the next thing that's happening is your first black holes form, and they produce this X-ray background, which gives you heating. All right, so that's going to give you a similar sort of fluctuations. The first black holes form in rare galaxies, so you get a strong X-ray background near those galaxies and hot gas, whereas gas far away from the first galaxies remains cool. All right, so you have strong temperature fluctuations, but to feed that into the 21 centimeter background, you need to combine that with your Lymanalpha fluctuations, all right, which are still occurring at pretty close in time. So you get a lot of Lyman alpha photons near those galaxies where you have hot gas. Okay? If you look at the temperature factor in the signal, it's proportional to spin temperature minus background temperature over spin temperature. So if this spin temperature is very hot, right, then this whole thing just goes to unity. Contrast that with if spin temperature is small, okay, then you get basically 1 over spin temperature here. And so the absorption signal can get arbitrarily large. The emission signal is small. And so you get relatively weak fluctuations when these two things are combined, because you're only seeing the hot emitting gas compared to the invisible gas out here. That gives you weak fluctuations. All right, so I lied a little bit before. In this particular model, what causes this turnover is actually this second effect, that the hot emitting gas has a smaller contrast than the cold gas that preceded it. So you get a turnover in your fluctuations when the heating just begins. All right, but soon you get saturation in this Lyman alpha background. Okay, so you get cold absorbing gas far from the first sources. You still have your hot emitting gas close to the first sources. And you get a huge contrast between emission and absorption. All right, so once this phase kicks in, you get a big increase in your fluctuations. Again, the solid line here is what I'm talking about. All right, but pretty soon you build up an X-ray background everywhere, and so you get hot emitting gas everywhere. Once this gas is hot and emitting, you get spin temperature over spin temperature. It saturates. Okay, you don't care about the actual temperature anymore. It doesn't matter that it's hotter here than out here. All right, everything's hot enough to give you the same signal. So again, you're going to get a decrease in your fluctuation amplitude once everything is hot. All right. So you get features in the monopole. You get the same kind of features in the fluctuations. The difference with the fluctuations is actually you can map out those first sources of light. OK. So let me just finish up by mentioning reionization and how that affects things. So it's destroying the neutral gas, and so you expect to get fluctuations as your H2 regions blow up. Okay. So this is the power spectrum as it evolves during reionization. And the nice thing is you get a lot of evolution in the statistics in addition to the maps. Okay, so this is actually what the experiments that I've already mentioned are aiming to do, is to measure the power spectrum of the 21 centimeter background during reionization. All right, so I will just finish with this, which is a simulation of the 21 centimeter signal from redshift of 200 through reionization. So here at redshift of 80, you're just starting to get the first galaxies form. Pretty soon you're going to see this jump up. So this is the Lyman alpha background kicking in. This is the X-ray heating. All right, then the signal falls again. And then as these black blobs grow, that's reionization. It gets big again, and reionization finally kills it off. Okay? So there's a whole lot of structure to this signal over time. And what we want to do is basically make these kinds of movies eventually. Right now, we're just going to be doing the movies of the statistics. Okay? But we're hoping to pull out a whole lot of astrophysics from this particular transition. Okay? So I'll stop there.
This program is brought to you by Caltech. Visit us at caltech.edu.